Hello, it's my pleasure to speak on the topic of a LENR reference experiment. And my talk is structured in 4 parts. The first part directly speaks to the objective of ARPA-E in the context of this workshop, which has been phrased as follows: to support targeted R&D towards establishing at least one on-demand repeatable LENR experiment with diagnostic evidence that is convincing to the wider scientific community. So the first part of my presentation will address this question: what is diagnostic evidence that is needed here, that is convincing to the wider scientific community? To get there, we need to make sense of the variety of experimental configurations that have been proposed for LENR systems and also the range of relevant characterization techniques. And finally, I will discuss what this means for going forward by suggesting a combination of 2 approaches. One, a top-down approach based on extensive characterization of a small number of established LENR experiments, and another one, a bottom-up approach based on hypothesis-driven experiments rooted in known mechanisms for enhancing nuclear transitions. So one focus of the discussion around LENR systems is on reproducibility, which is very understandable given the historical difficulty with reproducibility in this field. But there's another dimension to consider here, and that is what I think Scott aptly called irrefutability, which is, in a sense, the opposite of ambiguity, meaning that there are a large number of alternative explanations for a observed phenomenon. And so this really leaves us with what I here call the reproducibility challenge and the irrefutability challenge. And just a short example to illustrate why we need to consider both of these dimensions, at least those 2 dimensions. If you were to move from this bottom left corner here, which arguably is the status quo today, with poorly reproducible excess heat, to highly reproducible excess heat, you may still expose yourself to a large number of criticisms because, say, for example, you have a LENR experiment where you, in this case, say you have a 10-gram, a relatively small sample, 10-gram producing, let's say, 10 milliwatts of excess heat, then you may have to run this sample for a long time to exceed the chemical limit, which we can assume here to be 100 kilojoule. And so even then, somebody might come and say, wait, perhaps you suffer from some systematic errors, such as heat leaking into your system or redistributing in your system and so forth. So you need to not only have high reproducibility, but also low ambiguity. And the way to do that is to use characterization techniques that give you more information about your LENR system than just heat output. And ideally so that you can also say something about what reactions take place and perhaps even what mechanisms drive them. So that means the goal is to move from this bottom left corner to this top right corner of high reproducibility and high irrefutability. So in order to better understand how to move there, we need to dive into what LENR systems are and how they can be characterized. Somebody first encountering this literature may find themselves confronted with a large variety of experimental configurations and also a large variety of different characterization techniques that have been employed in different experiments. Let's focus on the experimental configurations first. We'll step through a few major ones, and let me also show that they can be reduced to a common denominator from a big picture perspective. Namely, a solid-state structure is loaded with hydrogen in some way and then stimulated by applying energy externally in some form. And we can see that in the classical electrolysis experiments like the Fleischmann-Pons experiment. Bulk foils of palladium are loaded with deuterium via electrolysis, and then deuterium diffusion represents a form of stimulation here. In other experimental configurations, thin films are loaded with hydrogen via mechanical pressure and then stimulated with electric pulses. And in yet other experimental configurations, nanoparticles are loaded via mechanical pressure and stimulated with elevated temperature. Finally, there is loading of bulk materials with ion beams, for example, accelerated deuterium ions, which then get both implanted in the target and also stimulate the target. So we can add some structure with a simple taxonomy to the variety of experimental approaches in the literature. This is not necessarily exhaustive, but I think it covers the large majority of experimental configurations that have been proposed and described. But to really get to a fundamental common denominator of LENR systems, we need to look at what all of these implementations do at the nano level. And so let's zoom in here as to what we can expect at the nano level for each of these experimental configurations. And this is, in the most general terms, what we can find at the nano level in all of these systems. We have a metal lattice with some hydrogen atoms loaded into parts of it, but the lattice is likely not homogeneous. There are impurities in it, maybe alloying components. So we have to consider the lattice composition. And then there are defects in the lattice, such as vacancies, cracks, and grain boundaries. So we have to consider the lattice morphology. And finally, when energy is added to the lattice, it'll undergo a dynamic response. So we have some lattice dynamics to consider as well. So that's our lattice to start with. Now, another key feature besides the solid state environment is a large energy output, which is presumably nuclear in nature. And then the lattice, from the energy perspective, the lattice is really a repository of atomic potential energy and nuclear potential energy. And atomic potential energy is electronic binding energy, so chemical energy that gets released if your sample burns up, for instance. And nuclear potential energy is the binding energy between the nucleons in the nuclei of the sample. And when that energy gets released, the sample gets lighter in mass because of the equivalence of energy and mass, E equals mc squared. And then that energy needs to go somewhere. It comes out of the system either as energetic particles or as other kinds of dynamics induced, such as lattice dynamics. And at the same time, this must mean that there are some composition changes in the sample, since some of our elements will have changed. So let's look at our sample again, but now from a perspective of energy leaving the system. So you had a fusion reaction occur between two deuterium atoms in this vacancy, forming a helium nucleus. Then you have a release of 24 MeV of energy due to the mass difference. So one conceivable pathway is that this released energy leaves the system in the form of a single energetic particle, such as a photon. Another conceivable pathway is that the reaction results in charged particles, which then get slowed down by the lattice and eventually thermalize if they don't make it out. So in the end, they produce heat. Another conceivable pathway is that the released energy goes into dynamics of the lattice if they can be absorbed by a reasonably large part of the lattice. This could mean quite orderly vibrations of the lattice initially, but would ultimately also result in heat. There's also the possibility that an initial nuclear reaction triggers a secondary nuclear reaction, such as driving out an alpha particle from a lattice nucleus. Finally, there's the possibility of some of the energy going into breaking some of the chemical bonds in the lattice, which would result in cracks and destruction of the lattice. So there is a large number of potential effects that could result from a nuclear reaction in a lattice. Many of these effects will ultimately result in heat, but by the time you measure that heat, a lot of the interesting action is already over. So we should really distinguish here between different characterization modes and the degree to which they help us answer different kinds of questions about these systems. And I like to think of this as a ladder of characterization modes. And the deeper you go down the ladder, the deeper your understanding of the system becomes. And also the fewer the alternative explanations become that we need to contend with. So being mindful of the modes of characterization that are available to us and that are employed in a given experiment is critical in moving toward a reference experiment that is not only reproducible, but also unambiguous. Now, let's look at how these different characterization modes have been employed in the LENR literature to date to arrive at an assessment of the status quo. Again, the focus here is on seeing what kinds of data different characterization techniques have produced in the literature, not to draw conclusions from these reports. And we'll start with two papers where excess heat is prominently featured as a major output that was characterized. We'll then move to three papers that report the emission of neutrons and charged particles. Then we'll move on to three papers that focus on composition changes. There's three papers that discuss changes in morphology, and there's also two papers that are related to lattice dynamics and their changes. And we start with the classic Fleischmann and Pons cell, where a palladium foil cathode is electrochemically loaded with deuterium. Here's a calibration pulse that shows the performance of the calorimeter, and here is an excess heat burst that lasted many hours. Down here you see the integration of excess heat to arrive at a total energy released from that sample of about 20 megajoules. Here is a more recent example of a similar measurement. Here you have an alternation between control pulses and stimulation of a LENR system, which is reported to exhibit large excess heat output. Again, you can see the excess power integrated to get the total energy in versus out. Moving on to the detection of energetic particles, here you see a similar configuration reported as the Fleischmann-Pons cell, but now located above a neutron spectrometer. Here, the neutron counts before and after the run. The neutron spectrometer suggests a neutron energy around 5 MeV. There are also reports of high-energy charged particles. In this configuration, a palladium foil is bombarded with low-energy deuterium ions on the order of a few hundred eV. The authors then report detection of a small number of charged particles around 21 MeV. Finally, there's an experiment at MIT where we observed charged particles around 28 MeV from the low-energy deuterium bombardment of titanium foil. Moving on to composition changes, Gozzi et al. At the University of Rome reported the measurement of helium-4 correlated with excess heat production in a Fleischmann-Pons type cell, suggesting that the deuterium plus deuterium to helium-4 reaction is happening here. Next is an example where both a composition change and a morphology change is reported. In this experiment, a palladium thin film is irradiated by a laser in a pressurized deuterium atmosphere. After several weeks, a visible change can be seen at the surface of where the laser irradiated the sample. An elemental analysis suggests that the amount of palladium there has gone down, while the amount of lighter elements such as iron and zinc there has gone up. We see a similar report by a group at NASA after pressure cycling deuterium against palladium-silver wires. On the surface of the sample, spots could be found after the experiment that exhibit lower palladium and lighter elements such as iron and zinc, apparently. The conjecture has been made that this may be palladium fission as a secondary reaction driven by a deuterium fusion. We also see a morphology change reported in this experiment conducted by several Japanese groups with copper nickel or palladium nickel nanoparticles embedded in zirconium pellets, which are then placed in a chamber with elevated deuterium pressure and heated up to about 250 to 300 degrees C. After the experiment, the researchers report finding a substantial number of pellets broken or cracked. Finally, let me show you two examples of characterization modes related to lattice dynamics. In this experiment here, a palladium cathode is in an electrochemical cell loaded with deuterium and stimulated with terahertz photons from a dual laser configuration. Dozens of runs are conducted, each with a slightly different photon frequency. The results suggest that large amounts of excess heat only occur at certain frequencies of stimulation. This graph over here further shows that these frequencies appear to coincide with the vibrational modes of palladium hydride lattice. So this is a paper from the 1970s that's completely unrelated to the LENR literature. This is still not a direct measurement of lattice dynamics. To my knowledge, only a single LENR experiment has been documented where lattice dynamics were actually measured directly or attempted to be measured directly during excess heat production. And that is the experiment here reported by Swartz in 2017. To measure lattice dynamics, Raman spectroscopy is employed where a laser beam is reflected off a surface of a lattice, and the photons lose or gain some energy from the lattice depending on the vibration. So this example here shows a peak that indicates lattice vibrations at about 10 terahertz frequency in a silicon sample. This is not a LENR paper. This is merely for illustration of the Raman spectroscopy technique. But then down here, we see a Raman spectroscopy technique employed in this LENR experiment with reports of Raman peak going up during excess heat production, suggesting strong ordered vibrations of the lattice. Okay, now I've shown you how these different characterization techniques have been employed in the literature and the kind of data that was reported that resulted from this. There are two main lessons I want to draw from this exercise. One for the irrefutability challenge and the other for the reproducibility challenge. Basically, we have the irrefutability challenge or the ambiguity challenge because a large number of the LENR literature has employed characterization modes that offer a fairly large number of alternative explanations. In turn, there have been very few papers on those characteristics where few alternative explanations exist. That is something to keep in mind for a reference experiment. So the conclusion would be there needs to be more research using characterization techniques with less intrinsic ambiguity, so with fewer alternative explanations. And second, if we get back to this table to get an overview of these LENR experiments, we find that all columns have a large number of question marks in them. So that means basically when some things seem to have worked and caused any anomalous effects, we don't really know how to produce that system because we never precisely knew what that system looked like in the first place. So the second conclusion here would be the need to characterize and or control lattice and stimulation characteristics of experiments that show effects more comprehensively. So where do we go from here? We propose a combination of two approaches, top-down and bottom-up, like in tunnel boring, when you try to get through a very large mountain. If you come at this only from one side, you may end up getting too far from your supply lines. So you end up boring through the tunnel from both directions, and then of course you expect or you hope that you will have a breakthrough between the two approaches. In this case, the top-down phenomenological approach, that's the center of the discussion so far, and also a bottom-up first principles approach, which I'll talk about a little bit more later. As for the top-down approach, this could mean, for instance, having multiple groups repeat the certain decided upon experiments like this, for instance, take as a basis the Swartz 2017 paper, then characterize the sample composition and morphology, and correlate the results with excess heat observations as well as the Raman spectroscopy results. Similar kinds of research could be done with the Japanese nanoparticle samples as the basis. Aim for reproducing their results, add some composition analysis, add some Raman spectroscopy to the mix to reduce ambiguity. Let me now talk a little bit about a bottom-up approach, which I believe is also a very important counterpart to this. Here I present one example of a first principles approach, here based on the work of Peter Hagelstein at MIT. The basic idea is to build off mechanisms for enhancing nuclear transitions that are known in the literature. One is based on what is by today well-known principles of atomic physics, which is taking advantage of electron screening in a lattice environment to partially neutralize the repulsive Coulomb barrier. And in addition to that, the idea here is to benefit from couplings between nearby nuclei that are for a short time strongly enhanced by coherent quantum effects such as superradiance. So to illustrate this, consider first two deuterons in isolation, such as a deuterium molecule in a gas bottle. Per Kunin and Nauenberg's Nature paper of 1989, the spontaneous fusion rate then is about 10 to the minus 64 per second, so it's not observable. This kind of spontaneous fusion rate can be thought of as analogous to the spontaneous emission rate in quantum optics of a two-level quantum system. It's basically a probability distribution with a certain half-life, which can be thought of in this case as the average rate, the average reaction rate, or the average fusion rate, if you like. Now, if we add a palladium lattice around that deuteron pair, so we place the deuteron pair inside a palladium lattice inside a vacancy in a palladium lattice, then we can expect a screening potential on the order of 150 EVs, which drives up our fusion rate by about 15 to 20 orders of magnitude. This is still not observable, but we're getting closer to that. Okay, now we consider that our lattice also has some dopants. In this case, we choose U238 nuclei. Just adding the dopants by themselves, though, doesn't change anything. But if we now stimulate the system such that we get coherence, at least locally, for instance with laser photons, then we can get a coupling between the deuteron pair and a resonant nearby nucleus. And the uranium-238 nucleus is well suited for that because it has a high density of rotational states, around 24 MeV, and can therefore absorb the emitted energy from the D2 to helium-4 transition readily, which is about 24 MeV. And this leads to another substantial enhancement of the fusion rate. With a rate of 10 to the minus 10 per second, we're already in the regime that would correspond to the Fleischmann and Pons experiment. This has also been described in the Kunin and Nauenberg paper. Here's a simple way to help you build some intuition as to what might be happening here. Quantum systems are often visualized or illustrated through classical counterparts. And here the deuteron pair is represented by the orange oscillator. The state occupation probability then corresponds to the kinetic energy of the oscillator. The oscillator is weakly coupled to another oscillator that represents the U238 nucleus, as they're well known but weak electromagnetic couplings between nuclei. If the couplings between them are temporarily increased, for example by the laser stimulation, then excitation can move at an accelerated rate between coupled resonance systems. Here the uranium-238 nucleus disintegrated quickly after receiving the 24 MeV of excitation, resulting in alpha emission at 28 MeV. So that's the 24 MeV plus about 4 MeV. That corresponds to the mass difference of between the U238 nucleus and resulting thorium plus alpha nucleus. At the core, this is like flipping a high-energy qubit, exciting a qubit, which then subsequently falls apart because it cannot, it doesn't remain stable with upon receipt of this kind of excitation. So here you can see the result of this secondary reaction illustrated. So what you then have is you have both a change of effectively you have a change of your fusion products because the fusion reaction drives a secondary reaction, but you'd also have a change of other reaction parameters such as the fusion rate because the resonant absorption of the released energy facilitates the original reaction taking place compared to an incoherent reaction where the released energy needs to be absorbed by one of many weakly linked degrees of freedom. Exactly how we got the 28 MeV charged particles in the MIT experiments, and we have reason to believe that there are substantial amounts of uranium impurities in the titanium foil that we bombarded with low energy deuterons. But the explanatory power of this approach goes even further. Say if your lattice composition or your stimulation characteristics are slightly different, Then you might have another transfer of excitation, so a tertiary reaction before, or even farther, before the first receiver nucleus disintegrates. So this really would be related to the rate at which your transfers take place. If the following transfer takes place before the receiver nucleus has time to disintegrate, then you can have like this chain of transfer reactions going on, and the rate of transfer depends on both the composition of the lattice and also on the strength of the coupling, which in turn depends on the nature of the coherent stimulation. In this example, you would have a tertiary reaction such as neutron emission as a final result. This could explain the large variety of outcomes that seem so circumstantial to the particular experiment. But the key point here is the following. This bottom-up approach starts with a complete description of what your lattice ought to look like to generate any effects. In other words, for this approach, we start with a completely filled out characterization table. If we then create samples accordingly and they work, then we understand not just that they work, but also why and how they work. And for instance, we would be able to not make them not work anymore, which is also can be also quite powerful. With this approach, one can design even simpler versions of experiments that exhibit the same kind of mechanisms of accelerated nuclear emission, nuclear transitions, even if we don't go through the trouble of, say, tailor-made metal hydrogen systems with high vacancy content and so forth. So a simple version of an experiment could be, for instance, a single crystal iron-57 sample with some cobalt-57 dopants, where the cobalt-57 beta decay would continuously populate a number of iron-57 excited states. When this sample is then stimulated with coherent terahertz photons, generating also phonons in the sample, we predict enhanced coupling between nearby nuclei and Rabi oscillations, where nuclear excitation moves back and forth between resonant nuclei. And here we can connect to established recent literature. For instance, here you see results from a Nature paper that shows Rabi oscillations between coupled iron-57 nuclei. And here you see another Nature paper that shows enhanced nuclear emission from iron-57 nuclei. Okay, so where does all of this leave us? To summarize the key points here, a reference experiment needs to be both reproducible and unambiguous, irrefutable, if you like. Historically, emphasis has been on characterization modes that leave too much room for alternative explanations, such as heat. This leads to high ambiguity and low irrefutability. Going forward, one ought to prioritize characterization modes that are intrinsically more unambiguous, such as Raman spectroscopy for lattice dynamics, for instance. And then there are still too many uncharacterized, uncontrolled variables in any of the major experiments, so that is then no surprise that there is low reproducibility. To address these challenges, a future research program should pursue a two-pronged approach, consisting of a top-down approach that involves the comprehensive characterization of a small number of legacy experiments that ought to be very focused. And then a bottom-up approach, which involves simple experiments with precise specifications based on hypotheses about mechanism that connect with adjacent literatures on accelerated state transitions.